Okay, having described and reviewed Chapter 29 and the basics of calculating the force of a moving charge and a current in a magnetic field, we want to move on to Chapter 30. And in Chapter 30, we're going to talk about sources of magnetic fields. In your reading, you saw that there were two ways to calculate magnetic fields. Now, if you'll pause the video and at least write down a sentence or two describing the two ways to calculate the magnetic fields. The first way is the Biot-Savart law. And this is a way to take a current segment and from that current segment calculate the magnetic field. And then what we need to do is sum up all the current segments that contribute to that point, and that's the process of integration. So let's write the differential form for the Biot-Savart law. And pause the video and write it down. And of course, we have that the increment of the magnetic field, or the incremental contribution, is equal to the quantity mu naught, the current I over 4 pi, ds representing the direction of the current, and that as a cross product to r hat, which is our unit vector pointing to the point of interest, and all that divided by the distance between the current segment and the point of interest, r squared. Of course, you should be able to describe for yourself, just as I did, what each of the terms mean. What is ds, what is r hat, what does r squared mean, and what does the current mean? Now take a moment and draw a diagram indicating each of the variables. The ds, the r hat, and the r squared, or rather the r. And I show here a diagram indicating each one of the variables. I show ds, which is in the direction of the current. I show the increment ds, or the magnitude of it, and that's shown in red. I show r, the distance from the current increment to the point of interest P. I show the r hat vector, which is in green, pointing in the direction of P from the current segment. Now, using the right-hand rule, what is the direction of the magnetic field at point P? Once again, pause the video and see if you can figure it out. And I show the direction of the magnetic field, and that is in the direction out of the paper. Now let's look at Ampere's Circuital law. We've now talked just a minute about the Biot-Savart law. We're now going to talk about Ampere's Circuital law. These are our two ways of calculating magnetic field. And this Ampere's Circuital law is that the closed integral of B dot ds is equal to mu naught I crossing. And the reason I put the sub crossing is that we're looking at the current crossing the surface bounded by that surface integral. So let's see if we can draw a diagram. So I crossing is current crossing surface bounded by the closed line. And let's see if we can draw what line we're talking about. For a straight current carrying wire, we have the following. A straight line, and then we indicate the surface. And what we notice here is we have the boundary around the surface, and that's indicated in red, and the slight purple color indicates the surface And we show in the center the current coming through that surface being bounded by this red line. Now that is our integration area. We're going to integrate around that particular curve. We show ds, which is the direction tangent to the curve. That is our ds that's in our integral formulation. And we show the current going in the direction as indicated. Now we have ds and I. Our goal is to calculate b. And like I said, we're just going to talk about it this time. And we have certain conditions for using Ampere's law. One, b can be treated as a constant or constant magnitude and direction relative to the path of integration. One of those two makes the whole problem easier. And two, the geometry is simple or simple to integrate. At this point, we want to stop and we want to begin to actually use these two methods to calculate the magnetic field for certain circumstances. One of them is for different geometries of current carrying wires, and the other is for simple geometries where we can look at using a simple way of calculating the magnetic field, and that's using Ampere's Circuital law. So we'll stop here and go on to our first problem.